Hello guys, my name is Samuel D. Koidia. We're back again. Today we're going to interact with physics, and our topic today is going to be simple harmonic motion. Today's lesson is not math, it's going to be physics, and the topic is simple harmonic motion. First of all, I want to define what's the simple harmonic motion. Simple harmonic motion is the type of motion, it's a kind of oscillatory motion in which the displacement is directly proportional to the acceleration, and that acceleration is always towards the center of the circle, and that acceleration, that displacement too is going to be opposite the acceleration. So I'm going to give you some of the properties of the simple harmonic motion. Remember, I just said that it is the type of motion that is, first of all, oscillatory. It's an oscillatory motion. So we look at characteristics of SHM. Yeah, first it is oscillatory. That is, it's a to and fro. It's oscillatory, that is, it's a to and fro motion, right? And it is periodic. It's periodic. It means that it can repeat itself at intervals of time. That's what we mean by periodic. It's linear. It's linear, so it means it can also go in a straight line as it is moving like that. And its acceleration, the acceleration is directly proportional to the displacement. Yeah, the acceleration of the body is directly proportional to the displacement, and that same acceleration is opposite the displacement. Is opposite the displacement. So in other words, if the body is accelerating this way, the displacement is the other way. So that is basically and it's also circular. It's a circular motion. Yep, so now we have all these characteristics of simple harmonic motion. It's oscillatory, meaning it's to and fro motion. It is periodic, meaning it repeats itself at intervals of time. Now it's linear, it means it goes in a straight line motion. Its acceleration is directly proportional to the displacement. We should see that. And we have the acceleration is also opposite, meaning if it is accelerating this way, the displacement is this way, and vice versa. And you also have it's circular because it is a circular motion. It goes around the cycle. So now this simple harmonic motion will have examples. Let's say examples or systems that performs simple harmonic motion. Systems that perform simple harmonic motion. The first one is the simple pendulum. You have the simple pendulum. The simple pendulum. Yep, that is what we have here. That's what we're going to interact with much more. It's an example or a system that performs simple harmonic motion. That's what we call it, simple pendulum. I'll still describe as a simple pendulum for you. And you have a vertical vibration, vertical oscillation, first of all, by a spiral spring. Spiral spring. Some of you have seen a spiral spring. It oscillates to up and down. That's vertical oscillation by spiral spring. That's one example of simple harmonic motion. There's the tuning fork. The tuning fork is an example of tuning fork also performs simple harmonic motion. When you sound the tuning fork, it vibrates. It also moves to and fro. That's a simple harmonic motion as well. And this loaded test tube. Loaded test tube in water, or we can say U-tube, water in the U-tube containing water. So if you have a U-tube like this, it's a U-tube, there's the water in there. This is the tube, this is the tube. The water in there, we oscillate to and fro in the U-tube. And in the case of the oscillatory motion by loaded test tube, if I have a test tube inside the water, and it's as much as it's loaded with some pebbles, if you load it such that the pebbles allow the test tube to be vertical inside the water, you see the test tube begin to vibrate up and down. That's also a simple harmonic motion. And you have bifilar suspension. bifilar suspension. You see all of this very soon. Very soon you see them. Bifilar suspension. Bi means two strings suspending. So you have a metal roll and you have a string here on it, and this metal roll perform is on oscillatory motion. That's bifilar suspension. I will show you when I move along. So we have this basic and loaded test tube. You have pendulum. You have, if you used to have waves, or even waves. Waves vibrate in simple harmonic motion. Wave motion is simple harmonic motion. They trough on the crest and they also vibrate simple harmonically. So we have the simple pendulum, an example. They have the vertical oscillation by spiral spring. You know that already. So that is like I have a spring here. I have put a mass there. So you see this spring begin to vibrate vertically up and down. That's a vertical oscillation by spiral spring. Tuning fork. Tuning fork. You will see a tuning fork very soon. Here we have the tuning fork. If I sound it, the tuning fork will vibrate like that. Also oscillatory motion. And loaded test tube or U-tube. And you also have bifilar suspension that I just gave you. And waves. Wave also vibrate in simple harmonic motion. They move to and fro in that order. So wave motion is an example of simple harmonic motion. So I've given you these simple examples of simple harmonic motion. So now what we're going to do is to look at the examples of simple harmonic motion practically. So I'm moving now away from the concepts, from the theory. Then I'm going to apply it now. We want to see what is, first of all, the simple pendulum. What are the laws governing the operation of oscillation of simple pendulum? Very soon I'll get to that. So let me just clean here to see how we can move along. So we have already defined the simple harmonic motion. We have also described a few examples. So we now want to look at a specific example, which is the simple pendulum. So we'll look at a simple pendulum. And then a simple pendulum is a specific example. Yeah, so what's the simple pendulum? The simple pendulum is a string with a bulb at the end there, and this string is attached to a support, and this is the length of that string is from that point up to the center of gravity. Or to the center of gravity, the center of gravity, that's the length of that string. That is an inextensible string, and that string and the bulb hanging there, it's a simple pendulum. And the simple pendulum is attached to a rigid support there. And now this simple pendulum will oscillate, and we displace it, and it will oscillate. When you displace it, it will oscillate. As a matter of fact, so here, if it is going to be displaced at some angle, we see that there is a displacement somewhere there. So it is going to be displaced angularly. So we want to look at the displacement, and when you leave it, we are expecting it to come back here. So there's going to be a to and fro motion. That's what this is the equilibrium position. So it's going to be moving from one end to another. And in this case, there's going to be a transformation of energy. You see, there's going to be potential energy somewhere there, and as it is coming down, it is converting all that potential energy into kinetic energy, and the kinetic energy becomes higher at the middle here, and it goes up like that until kinetic energy becomes lower here, or goes to zero, and potential energy at the extreme is maximum. So we have PE is maximum in that end, and kinetic energy is zero at the end there, and in the middle here, kinetic energy is maximum in the middle, and potential energy at the extreme is zero, is maximum, sorry, and we have kinetic energy becoming zero at the extreme. So at the extreme there, we have the kinetic energy becoming zero, but the potential energy is going to be maximum here. So it means that all the kinetic energy is moving with is going to be transformed into maximum potential energy at that height. So as it is coming back again, the potential energy at that height is also converted to kinetic energy as the object is moving. So at the middle here, the kinetic energy becomes maximum and the potential energy becomes zero here. So here we have potential energy zero. So now we want to look at this is the effective length of there are terminologies that we want to actually define on the simple pendulum. We have first the effective length, that is the effective length. So terms, effective length. what is the effective length of a simple pendulum? The effective length is the length of the string, which is from this rigid support to the center of gravity of that ball. That is the effective length of the, so we need to know what's the effective length of that, and we also want to look at the period. The period, T, we said that is the time it takes to complete an oscillation, so we need to figure out that as well. We want to also look at the amplitude. We know that amplitude is the maximum displacement from the equilibrium position. So that maximum displacement from its equilibrium position is what is called the amplitude. And in this case, because the displacement is angular, we call it the angular amplitude. So this angular amplitude, the frequency, the period, we also lead to what is called the frequency. Those are terms that we're interested in, and that frequency is the reciprocal of the period, just like the period is the reciprocal of the frequency. So we have terminologies here that we have to interact with. First, the effective length of the simple pendulum, the period of the simple pendulum. The effective length is the point of suspension, like from there up to the center of gravity of the bulb. That's what's called the effective length of the bulb of the simple pendulum. It starts from that point over there, where the cork is hanging, up to the center of gravity, and this is the bulb, this is the string, and now we have a cork somewhere there. This cork is holding this string. It's there to just hold the string, and we have a whole rotor stand, that's the rotor stand, and we have the clamp and the bulbs. These are the bulbs, these are the bulbs, and we have the clamp, and we have the cork over there, and there is a string, and that string is attached to the simple, to the bulb, and collectively we call it the simple pendulum. And the length of that the effective length is where it is suspended to the center of gravity of the bulb. So you understand the terminology right now here. So we want to look at the laws that govern simple pendulum. So simple pendulum has laws. So we want to look at the laws of simple pendulum. Laws of the simple pendulum. Simple pendulum. So we have law number one. What is the law number one? Well, it's a simple pendulum. The law number one is the law of isochronism. Law of isochronism. Yeah, law of isochronism states that in the limit, if you cannot extremely go to a maximum amplitude, meaning if you cannot exceed a particular number, a particular angle, the period is going to be independent of the amplitude, right? If you don't go towards a particular value, so there's a particular value or a particular extreme that you can go, that this period of the simple pendulum will be affected by the amplitude. So that law of isochronism is that I have to ensure that the amplitude is not as large enough. If it is too large, then the period is going to be affected. So how do I know that I'm within the limit such that my period will not be affected? So I have to ensure that the angular displacement here, which is what we call the angular amplitude, or the amplitude there, that angular displacement, we have to make sure that it is within a particular limit. Beyond that limit, like for instance, if I displace it, that's the angular displacement. If it is to an extreme, then this law will be affecting the period. So it means this particular maximum displacement will affect the period. So if I don't want the period to be affected, then I have to give it a particular angle. I have to get a particular displacement angle to ensure that the period of the simple pendulum is not affected by the displacement. So how small is small? In the exam we say what is displace the ball to a small amount. Then what is small? How small is small? So we need to know what to which limit do I need to displace this ball to ensure that I actually have it as a non-factor to affect the period. So if the displacement is to an extreme too much, you have to affect the period there. And we want to know whether we can adjust what particular angle to which, or what displacement level can we actually displace this simple pendulum to ensure that the period is not affected. And to do that, we needed to know to which angle. Now, it's in terms of some research have discovered that the maximum angle here will be 10 degrees. If I displace it at an angle approximately 10 degrees and below, that is that. So it's possible that the displacement of this bulb will not be a factor to the period. But if I go to above that particular value, it's going to affect the period. So how do I ensure that the period is not affected? So I have to actually know to which level or to what amount am I going to displace this bulb. Is it going to be a maximum displacement, or is it going to be a small displacement? So how small is small? So I need to know, and for convenience, and they have got a lot of research on this, it is advisable to get it at an angle of 10 degrees and below. So let's say that's 10 degrees. So now the student cannot take a protractor trying to measure this angle here. It will be difficult for that student to do that, so that it's difficult for you to get the displacement angle as 10 degrees. So what you do is, what I will advise you to do is, let's do the math over there. Let's say that's the bulb. That bulb is displaced there, and it's now displaced at some angle. That is that angle. They say it should be it's approximately, it is irrelevant. If you take 10 degrees, it will be reasonable. So now let's see the length of the spring. The string is that. So now I'll find to what displacement do I have to actually push this string, either this way or the other way. At what angle? This angle will now give me this displacement, within which I will ensure that the period is not affected. So what is that angle? So let's say I'm using a string of length 80 centimeter, like these ones here. These ones I've measured this to be 80 centimeter. So let's see, that is that limit. So I have the angle here. The angle is advisable. You can take 10 or below 10, but it's not advisable to go beyond 10. So let's see, that is the angle is going to be opposite over hypotenuse. So I have sine 10 is equals to, the opposite is x all over 80. So if you punch the calculator, you have x is equals to 80 sine 10. So if you use your calculator, you will find out that sine 10, 80 is multiplied by 0.1736. If you have your calculator, 1736. If you punch that properly, you will have something like 13.8. So you have 13.8 and 13.8 centimeter. So 13.8 centimeter. So this 13.8 centimeter is this displacement to which I can displace the ball to give me a reasonable value that will not affect the period. So how do I relate this one to the displacement? Because the students will not be able to have the protractor to find that angle. So now you are advised to compare this distance with respect to the angle. So let's say the length of this thing was 80. Now I want to compare it. You know, the length was 80, and this displacement is 13 point that. So let's say 13.8. So if you punch that, you have something like 5.7. So 5.7 centimeter, and that is approximately 6. So now it's telling you that if I displace the bulb 1/6 of the original length, then I'll be within that limit. I'll not be able to commit this crime here by extending the pendulum to a bigger amplitude. So it is 1/6. So if I want to find the amplitude now, the angular amplitude or angular displacement, or the maximum displacement, if we want to call it that way, we can say it. Sorry, we have the maximum displacement. The maximum displacement of that bulb will now be 1/6 of the length given. So let's say this length is 80, so it's 1/6 of 80 centimeter. So 1/6 of 18 centimeter is somewhere around 13 point something. So 13.4. So let's say approximately 13. So if I displace this, the amplitude, at 13 centimeter from the equilibrium position, I'll be in a reasonable position that will make sure I will not commit this crime called the isochronism. So the law of isochronism is telling you that you have to be within a particular displacement to ensure that that displacement will not affect the period of the simple pendulum. So now it is 1/6 of the, so if I'm going to use this as an example, this is 80, I'm supposed to displace this ball at let's say approximately 13 centimeter from the equilibrium position. So from the equilibrium position, I measure 13 centimeter. That is where I'm supposed to displace the ball, not more than that, because if I go beyond that, I'm going to be affected. It's going to be affected by the isochronism law. So that I must ensure that I'm within this limit. That will give me a reasonable value that will make sure my experiment is not disturbed. So now that is first law. What about the second law? So I go to the second law. The second law is the law of length. Now, the law of length states that the period of a simple pendulum is directly proportional to the length. Yeah. So it means that as I'm increasing the length, that's how the period also going to increase. That's the square root of the length is directly proportional to this period. That's another law. Number 3 is the same period we're trying to investigate. It says that it is inversely proportional to the square root of the acceleration due to gravity. Inside the studio there is gravity, so the acceleration due to gravity is also a factor that will affect the period there. And we have the other fourth factor, which is the law of length. This is law of acceleration. This is law of acceleration. Law of acceleration. Yes, which says that the period of the simple pendulum is inversely proportional to the square root of the acceleration due to gravity in this case. So here we'll have also the law of mass. The law of mass M. It says that the period is independent upon the mass. We'll soon prove that independent of the mass of the ball. The mass of the ball. So we'll soon prove those 4. So we now look at this. Since this is independent, so we can now put the 3 together that are connected. This is the length is directly proportional to the square root of the period is directly proportional to the square root of the length, and the same period is inversely proportional to the square root of the acceleration due to gravity. So we can now put the 2 in perspective, and we'll try to connect them by joint variation. This is L all over G. So by extension, we'll now have, if we move the proportionality sign to this, a constant. That constant is 2 pi, and we'll have L over G. So the period of the simple pendulum is given by this relationship. So it is all the factor, and here this is 2 pi is a constant of proportionality. It is with respect to radial circular measurement as a constant of proportionality. So we now have the period connected to these factors. So if the length is a factor, we want to see what this length, if the mass is not a factor, they will also want to see how the mass, if I change the masses of all of this, what will happen to the period. That is, we said we are coming to investigate something. We said the period is directly proportional to the length. So I'm going to change all of this, and we see how the period is affected, so we'll know. And I'm also going to change the amplitude and see whether the amplitude is a factor within this limit. And we are also going to see how the mass is an independent variable in terms of this period. So that is basically what we are coming to do. So we now move towards the practical. So I just give you one more a summary of what I've said. I'll be able to give you the times that we're going to interact with. We said the length of the simple pendulum, the period of the simple pendulum, the amplitude, the frequency. You know that frequency is the number of times you do something within a particular period of time. The number of times you do stuff. So the number of times is going to be swinging. It's going to be a relationship with the period. That's why we said it is inversely proportional to the period. Now we have the laws of the simple pendulum. We said there is law of isochronism, which tells you that if you displace the simple pendulum to a very high displacement, the period will not be, this equation will not be supported. It means that you'll be out of this relationship. So for me to be inside that relationship, I must ensure that I don't have a bigger displacement that will make sure that I move away from this connection between these factors. So what is the reasonable angle to which I can displace this? We said that you can try 10 degrees or more, and if you cannot use the 10 degrees on the pendulum in the practical room, you can use this approach. So I try to do some trigonometry stuff here to be able to get this displacement. So I use this trigonometry sign, that's SOHCAHTOA, it's opposite over hypotenuse, that's the length, is the hypotenuse. So I was able to get the displacement as being equivalent to 1/6 of the length of the pendulum. So as I'm changing the length, when I want to displace the length, I must ensure that I take the displacement as 1/6 of this length I'm going to take. So if I have 90 centimeter here, if I want to displace it, I'm going to divide 90 by 6. That value is to which I will displace it. If this length is 30 centimeter, I'm going to take 1/6 of 30 centimeter. That's 5 centimeter. That's to which I'm going to displace it. This law is very important because it will affect the whole stuff. So that's the more reason why we go with that. So now we have seen the laws. We want to now go to the practical stuff.